In this example, we'll sketch the graph of the rational function f of x equals x minus 2 divided by x squared plus x minus 2. To sketch our graph, we need to find the y-intercept, the x-intercepts, the vertical asymptotes, and the end behavior. Let's start with the y-intercept because that's the easiest. For the y-intercept, we look when x equals 0. This gives us f of 0, which up top is 0 minus 2, and down bottom is 0 squared plus 0 minus 2, giving us negative 2 over negative 2, which is just 1, which means that the y-intercept is the point 0, 1, which we can plot on our graph. For the x-intercept, we need to look when y is 0. So we need to solve the equation 0 equals our function, which is x minus 2 over x squared plus x minus 2. But for a fraction to be 0, we need to make sure that the top is 0. So we just need to solve 0 equals x minus 2. To understand this, we would just multiply both sides of our equation by the denominator x squared plus x minus 2. On the left we just have 0, while on the right we'll have the numerator x minus 2. Now that we have this equation, it's easy to solve by adding 2 to both sides, giving us that x equals 2. So the x-intercept is the point 2, 0. Now for the vertical asymptotes, we want to find when the denominator is 0. X squared plus x minus 2 equals 0. And we can solve this using the quadratic formula. If you'd like to see the steps of that done out, you can click the link to the left now. Solving x squared plus x minus 2 equals 0 gives the solutions x equals 1 and x equals negative 2. So this means that we have vertical asymptotes on the lines x equals 1 and x equals negative 2. Finally, we need to figure out the end behavior of our graph. That is, what happens to our graph as x gets really large, going to positive or negative infinity. We saw that since the degree of our polynomial is bigger in the bottom than it is up top, the fraction as a whole just looks like 0 on the ends. This is because the bottom is growing much faster than the top, and so the fraction itself is getting very, very small. So we can put in that our function looks approximately like y equals 0 on the ends. Now to complete our graph, we need to check if our function is positive or negative on some of our intervals. This is because we know there are no more x-intercepts, so f of x can only change sign at the x-intercepts or at the vertical asymptotes. To check the interval of x values before negative 2, we need to pick an x value back there, say negative 3, and evaluate our function. F of negative 3 is negative 3 minus 2 over negative 3 squared plus negative 3 minus 2, which when we simplify is negative 5/4. So this means since the y value is negative at x equals negative 3, all of the y values must be negative to the left of negative 2. Because if it was positive somewhere, we would have to have an x-intercept to cross from negative to positive. Now using that all of our y values are negative, and as x goes towards negative 2, it gets infinitely large, and as x goes off to the left, it gets closer and closer to y equals 0, we can fill in this part of our graph. Now, for the interval between our two vertical asymptotes at x equals negative 2 and x equals 1, we have the point 0, 1 already, which means that we have a positive y value, and so all of our y values must be positive. But also, at the asymptotes, our function must increase to infinity. So we can use this to fill in our graph between negative 2 and 1, passing through the point 0, 1, not crossing the x-axis, and going off to infinity near the vertical asymptotes. Next, we need to look at the interval between x equals 1, our vertical asymptote, and x equals 2, our x-intercept. So let's pick x equals 1.5. And again, evaluate our function at 1.5. To compute f of 1.5, we do 1.5 minus 2 over 1.5 squared plus 1.5 minus 2, which is approximately negative 0.29. The most important piece here is that our y value is negative, which means that between 1 and 2, our y values are always negative. And because we have a vertical asymptote at x equals 1, it must be going down to negative infinity there. Finally, we need to check our x values beyond 2. To do that, let's try 4. Evaluating our function at 4, we get f of 4 is 4 minus 2 over 4 squared plus 4 minus 2, which is roughly 0.11. The important piece of this is that, although it's very small, it is positive. So our function must always be positive for x values beyond 2. And since we know our end behavior is that our function looks like 0 on the ends, our graph just comes up over the x-axis a little bit and hovers right above it. And we now have a graph of our function x minus 2 over x squared plus x minus 2.